It's a pleasure to continue. Wait, where's the chalk? Right, so today I'm going to tell you about something in this 2D theory of gravity, JT gravity, which a lot of people have been working on these days. And I think the primary motivation to work on this theory is just because it's extremely simple, so you can understand everything. But I'll try to discuss ways in which it may or may not be a good model for the real theories of gravity and string theory in higher dimensions. So it has, in some ways, it's an oversimplified model. But one of the motivations here is to see what will you have to add to it to make it into a better model for higher D gravity. So let me start by telling you what this theory is. So it's a theory of a metric and dilettante in 1+1 dimensions, which has the following action. This is the most important piece, so I'll write that first. Whoops. Okay, so the equation of motion of this scalar just sets the curvature to be -2. So it gives you constant negative curvature spaces. And then the equation of motion you get by varying the metric. So the equations of motion are r equals -2, and the equation of motion for the varying the metric gives you this matrix, 2x2 matrix of differential equations for the dilettante. And that also locally completely fixes the dilettante. So this theory has no locally propagating modes at all. And we're free to add to this, well, first of all, if I have boundaries, there's kind of a natural boundary action where gamma is the induced metric on the boundary, which takes this form. So if I have some boundary, it's natural to include a boundary action like this. So I'll sort of define the theory in that way. And then we may impose additional boundary conditions, either set, phi fixed, the metric fixed, or the conjugate variables. And then you're also free to add another term, which is topological term, the usual Gauss-Bonnet term. That takes this form. That would be if I had this action, that would look like the direct analog of the Einstein-Hilbert action in 2 dimensions, but of course it just computes the Euler character, and so it will not give me a non-trivial theory. In fact, it's not really consistent to take just this action because it doesn't depend on the conformal factor for the metric, which would be an unconstrained variable. So unless you gauged wild transformations, it wouldn't really make sense. But once I add this scalar, it eliminates that conformal mode because it fixes the curvature to be a constant. Okay. Excuse me. One way to motivate this action is if I started in higher dimensions and I looked at a near extremal black hole. So, for example, if I had 3D gravity in a space that looked like that manifold times a circle, then you can think of the radius of this circle will be some function of this manifold, some warp product. And we can think of that as being roughly this phi 0 number plus phi, which is the dynamical field. So phi 0 is a constant, and phi is one of the fields of the theory. So if I took 3D gravity and I reduced it to 2D on a circle, and I kept track of the radius of the circle, then the 3D Einstein-Hilbert action would reduce to this object if I ignore the higher KK modes. So it's some kind of truncation. Yeah, and if I did this, I would also get. Yeah, that's right. I would also have a gauge field, but I'm going to throw that away here. Yeah, because in the end you're in 2 dimensions, this gauge field will not be interacting in a non-trivial way with the rest of the theory, at least in the long distance limit. So we'll just study this extra truncated version, and it's sort of this truncation is physically relevant if we had the extremal black hole, the near horizon would look like ADS2 times some internal manifold. And the effective physics in this ADS2 factor will look like JT gravity, where the dilaton is, again, the size of this internal manifold. So that's where we might fit it into a bigger picture. But in my talk today, I'm just going to stick with this 2D theory, and I won't be interested in whether it might have come from something in higher dimensions. So that's just maybe if you wanted to connect it to other things. Now, it's well known that in ADS2, if I have the usual ADS2 boundary conditions, it's too constraining, and the only solution is the vacuum solutions. Then I won't be near extremal. I'll just be exactly extremal. I'll just sit in rigid ADS2. It will be too boring. And the usual boundary condition would be the one where, let's say I draw a picture like this. Let me draw a Euclidean picture. I might fill in the circle with the disk, and I might imagine that I put a boundary condition here where I fix the metric in the dilaton. That seems very natural. And then I'll take the metric to be scaled out to infinity. That would be the usual ADS boundary condition. So it would be something like that the metric on the boundary will be some value that I'll scale to infinity. So I'm going to take a limit that RC goes to infinity. And the usual ADS type boundary condition would, if I take phi on the boundary to be some constant in this limit. And that's the thing which is the bad idea, because if I do this, I end up finding only vacuum solutions. So it's too restrictive a boundary condition. And in fact, if I went back to this picture, it seems well motivated to pick a different scaling, because in the near extremal black hole, the size of the internal manifold also grows as you move away. So a better choice of boundary condition is to also scale the dilaton at the boundary to infinity with keeping this ratio fixed. So phi b is kept finite, and then I scale RC to infinity. So that's the boundary condition that defines sort of an interesting theory which has excitations on top of just the vacuum. So this is what people call the nearly ADS2 boundary condition. So we're going to study JT gravity with these nearly ADS2 boundary conditions. As I said, it has no locally propagating modes, so everything is about the analog of the boundary gravitons. So we can rephrase the whole theory. Let's say we're in Lorentz signature. This is supposed to be a picture of global Lorentzian ADS2. And then, well, since I'm in 1 + 1 dimensions, there has to be two boundaries. Here's one, here's the other, so here's the spatial slice. And then the only non-trivial dynamics are the locations of these boundaries in this global ADS2. Yeah, here I'm in Lorentzian. So, and similarly, in this picture with the disk, I can think of the Poincare disk, and then the non-trivial variable is where does the boundary live as a circle in the Poincare disk. So it's all about the boundary modes. Now, I'm going to first briefly review how one could analyze this theory in Lorentz signature in a very conventional way. So basically, you do canonical quantization of this theory of gravity. It's very easy to do that. And let me first describe how that looks. Okay. So what's the Hamiltonian in this theory? So as usual in gravity, the Hamiltonian is a pure boundary term. We have some analog of the ADM Hamiltonian, which turns out to be given by the following expression, where n is the normal derivative to the boundary. Okay. Now, what do we do with this theory? It's pretty trivial, because yeah, we'll take RC to infinity, but we can imagine RC is extremely large, but not quite infinity, and take it to infinity at the end, if you like. So, as usual in boundaries Hamiltonian, or the boundary stress energy, is defined with this factor removed. So we might say that this is equal to RC times the boundary quantum mechanics stress energy tensor. Well, which has only one component because we're in the boundary is 0 plus 1 dimensional. Okay? So if we discuss this in the context of ADS-CFT, we would think there's a quantum mechanics where the Hamiltonian is finite, which is dual to this gravity theory and that scaling limit. Okay. Now, what do the solutions actually look like? Well, in this picture, is actually slightly wrong. Where I drew the boundary is not exactly where it will sit by those equations of motion if I solve them at the classical level, because it looks like in this picture I could send causal signals from one boundary to the other. It turns out when you solve the equations of motion that you get for the boundary location, or, I mean, of course you can solve this theory in different ways. You could fix the gauge, solve it in sort of the bulk picture. You could fix the gauge in a different way, so it looks like equations of motion for two boundary points. Of course, you get the same answer either way. And the result is that let me just write for you the solution. So what does the classical solution look like? The classical solutions all look like two-sided black holes. So there's some choice. I mean, one can write it in many different coordinate systems. Let me write it in a coordinate system to start with that emphasizes that it looks like a black hole. Okay, so that looks like the 2D Schwarzschild metric, and the dilaton profile is a linear function of this radial direction. Oh, sorry. Can you see better there? Okay, good. Okay, so we have a solution that looks like this, and if we drew the Penrose diagram, it would look like the usual ADS-Schwarzschild Penrose diagram, where the two boundary positions sit here and here. Okay. Now, of course, in this 2D theory, there's no singularity where I drew this line. But if we go back to this motivation, then the size of the internal manifold was supposed to be phi 0 plus phi. So if phi goes to minus phi naught, something is singular in the higher dimensional picture. And so by fiat or extra ingredient, we can say that we should end the 2D space when phi reaches minus phi naught. And we're always going to imagine that phi naught is a very big number. Okay, so we always imagine we're in a regime where phi naught is much bigger than 1, and the phi profile is small fluctuation around it. That's sort of this logic of a near extremal black hole. Phi naught is like the extremal horizon size. Okay, so that's why I draw this wiggly line up here. Actually, it probably goes more like this if we want to make the picture more precise, but anyway. So it has the structure of a two-sided black hole. And in particular, you never get the configuration like this one where you could send something from one boundary to the other. That's not a solution of the boundary equations of motion. Why do you say that? Oh, if I have this condition. Yeah, sure, that's true, but I mean, at the level of the classical theory, you know, look, we could say, you could implement this by saying that there's some modification in the action when phi goes to negative phi naught, which is extremely tiny when phi is positive. And in the classical solutions, outside the horizon, phi is positive everywhere, so the correction to the equations is arbitrarily small there, and it's set by a new parameter that has no relation to S naught or the other parameters. Okay? So that's sort of the logic. So we could say this is an extremely good approximate solution. Okay, so how should we analyze this problem in a little bit more detail? Well, no, well, I wouldn't call that a gauge choice because usually usually at least when I think of the boundary conditions in ADS in general, I imagine we just fix the metrics, right? So So this is meant to be a boundary condition, and there's no, I broke the diff symmetry on the boundary. So the boundary is some quantum mechanics. I didn't gauge diffeomorphisms there. Of course, you could, well, semantics, but I just chose that. Yeah, I just chose that. Now,
what region?
Well, if you track this solution, since phi is proportional to r, in the region of the metric where r goes to negative values, which is behind the horizon here. So as we go this way, r goes to more and more negative values, and eventually we'll hit the place where we say that we stop trusting the solution. Okay, but I mean, whether we say we cut the space here or not is pretty much irrelevant to the discussion, but it's just to make the picture look more analogous to the black hole in higher dimensions. That's right. Yeah. I mean, this is at this line is sort of at r equals to r cutoff, which is the value that was set over there, and the other side is the same. I mean, this coordinates cover only this patch, right? Yeah. But I'll also write the same metric in different coordinates a few times. So. Okay, but I want to go somewhat quickly through this part because it's very simple and just to review. Okay, now in this particular metric, you can evaluate the ADM Hamiltonian that was written over there, and it turns out to be twice phi h squared over phi b, where phi h is the value of the dilaton here at the bifurcate horizon. Maybe you can't see it, so I'll push it up. I'll skip the one in the middle. If I use this part, is it okay? Okay, good. Right. Okay. So we could say that's the theory. Well, let's suppose we want to quantize this theory, quantize the phase space. What is the natural variable to discuss this solution? First of all, what is the dimensionality of the phase space? The ground state is the extremal black hole, which corresponds to phi h equals to 0, yes. No, that is allowed. Well, no. Phi h goes to some big negative number. Phi goes to some big negative number is not allowed. Yeah. Right. Okay. So a nice way to try to fix the gauge in this 2D gravity is to demand that the spatial slice has zero extrinsic curvature. In other words, that it's a space like geodesic. So we have our Penrose diagram of the space that looks like this. We can take, oops, this was supposed to cross there. Sorry, terrible picture. There's the horizons, and then I could take a slice like that at t equals 0. And then if I evolve up in time, that means evolving up in time on both boundaries. So I can look for a spatial slice that connects the two boundaries at a later time, which is still a geodesic, and these geodesics will look something like that. Okay, so we might call this geodesic gauge. In this context, conformal gauge or whatever. And it's easy to see that the only variable in the problem is the length of this geodesic. Now, what do I mean by the length? Because I'm going to take this limit that RC goes to infinity. They take the boundary out to infinity, the length is infinity. So we have to regularize the length a little bit, as usual in ADS context. So we'll define a variable that I'll call L, which is the actual length, minus the value I would have gotten in the zero energy extremal solution, which turns out to be minus 2 times the log of twice the value of the dilaton at the boundary. Okay? So one more, though I don't want to belabor this too much. I mean, one way to do this, one way to sort of compute this length and rewrite it in terms of the other variables, use slightly different coordinates, which cover the full space. Because it's not very nice to use the Schwarzschild coordinates to compute the length of this line, because they have two boundaries.
You take it to the law.
What?
The law, what do you think?
Oh, well, phi and the two boundaries is the same value. That was just by choice. In general, I would have had okay, but I assume they were equal to put it to. Okay, so when you compute this length, one way to do the computation is to use the global coordinates, where we can write just the ADS2 metric in global coordinates like this. And in terms of those coordinates, the dilettante solution takes this form. And then you can evaluate the length of this geodesic and find that the bare length is an integral from the cutoff values in these x coordinates, the x over 1 over square root 1 plus x squared. And when one goes through all the algebra, it turns out the answer has this piece, which looks divergent when you take RC to infinity. And when I subtract it off, the remainder is the following thing written in terms of the variables that we already discussed, and one that I'll explain in a second. Okay, so E is the energy, the ADM energy that we defined before. What's the little delta? Well, an obvious way to describe the configuration is, again, remember this, there was sort of a unique solution with a given energy if I look at it as a global spacetime. This, sorry? E is the ADM mass. E is H, yeah. All right, we can relabel it H. And so the solution seen from the global point of view is labeled only by its energy H, because the only free parameter was phi H. But of course, there's a choice of what time I take this slice. So I can call this time delta. That's the little delta sitting there. Okay. Now, if I want to quantize this phase space, I need to know what's the symplectic form. But it's kind of obvious in terms of H and delta what the symplectic form is, because H is supposed to be the generator of time translations, and delta is the time. So it better be that H and delta pair up in the symplectic pairing like this. Okay? Otherwise, H wouldn't be the generator of time translations. And then you can work out what is the conjugate momentum to this variable L. And it turns out the conjugate variable is given by the following formula, also relatively simple. Actually, when we first worked this out in a paper with Dan Harlow, we had a typo, like a factor of 2, and it's screwed up the results. So it was sort of conceptually similar, but the formula we got for the Hamiltonian looked a lot uglier than it should have been. And it was actually Henry Lin who pointed out this typo to us, which fixed the answer to a much nicer answer. Okay, so in terms of this L and P, they're canonically conjugate, and now we can rewrite the Hamiltonian in these natural variables. Should I write bigger? Would it be? Is there? Yeah. Okay. I'll try to write a bit bigger. Okay. So in terms of these variables, the Hamiltonian turns out to be just Liouville quantum mechanics. Potential like this. So it has an exponential potential e to the minus L. So what does that mean? So first of all, it sounds physically reasonable because the configurations all look like, so what are the classical configurations with a Hamiltonian like that? They look like scattering. So I send in things from L equals infinity with some momentum, a minimum value of L, and I get reflected off of the potential and go back out to L equals infinity. But that's exactly what the two-sided black hole looks like in terms of the length of the slices. At very early times, the slice is enormously large. Down here near the past, in the past, it's enormously large. It decreases approximately linearly until we start reaching somewhere near the middle, and then it turns around and starts growing again. Okay? So these problems just match, of course. Oh, no, L is not positive definite because I subtracted this piece, so it's ranged from minus infinity to infinity. Yeah. So this very simple theory of gravity is just Liouville quantum mechanics. Actually, there are other ways to see the same fact. There's a relation between JT gravity and SL2R BF theory. And if you translate the ADS-type boundary conditions of JT gravity into the BF theory language, they turn into, this reduction of SL2R, which is familiar in WZW models, where it gives Liouville. Here, it gives the Liouville quantum mechanics instead of Liouville CFT. Exactly. Yeah.
Where do I see this constraint?
No, you don't see that in this. You don't see that. That really plays no role here. That was just to motivate drawing the squiggly line, but the squiggly line didn't appear in any equations. So, from the point of view of maybe we could say, why did I not take this Penrose diagram and continue it to another piece on the top? And maybe that would have confused me, and I would have said there's some extra asymptotic region or something. It was to avoid that. But you mean why doesn't the Hilbert space look like a tensor product of a left one and a right one? Yeah, I'll have a bit to say about that in a minute. Okay. In fact, that's exactly what well, maybe before I get to that, let me just say another statement, which is I will, in not too long, also discuss Euclidean analysis of this theory. And when one does the Euclidean path integral in this theory, it seems very natural to also include the sum over topologies. And that makes the Euclidean theory much richer and more interesting. And a lot of some of what I want to talk about is how to reconcile the Euclidean analysis where you sum over topologies with something in Lorentz signature. Of course, if we just look at these Lorentzian pictures, it's not possible to change the topology right there. I can't draw some handle. There's no such Lorentzian manifold. It seems mysterious. But part of what I want to discuss is how to kind of reconcile those pictures, and I'll come to that a bit later. Okay. Is there a clock in here? Okay. Yeah, 2:01. All right. Okay. Oh, boy. Well, kind of a complicated formula, but it's sort of like, it's the change of coordinates between the Rindler patch of ADS2 and global coordinates. But, let's leave that as an exercise. Okay. So as Zohar said, something here seems strange if we think about it from the point of view of ADS-CFT. Because you might have thought that this JT gravity was, low energy approximation to a theory of gravity or string theory or something, which was dual to quantum mechanics. And if we study this thing in a setup with two asymptotic boundaries, you would have thought the Hilbert space would be a tensor product of two copies of the quantum mechanics Hilbert space. So.
You would normally expect
well, I would say this quantum mechanics has too many degrees of freedom because the spectrum is continuous. So it actually has too many states. It has a continuous spectrum. Whereas you would have thought that the quantum mechanics has this very dense degrees of freedom in the sense of variables in the phase space is not really meaningful, right? I mean, if I can always add some other directions in the phase space with size h bar, and it doesn't change, So that's not really the problem is that I get a continuous spectrum, and the Hilbert space doesn't look factorized. Those are sort of two obvious problems. Let me talk about the factorization point first, and then we'll come to the continuous spectrum aspect. Okay? Oops. Right. So you might have thought that it was supposed to look like a boundary quantum mechanics on the left, tensor with the boundary quantum mechanics on the right, but this Hilbert space doesn't take that form at all. It's just a bunch of scattering states of alluvial quantum mechanics. Moreover, if we tried to compute the entropy of the thermal entropy of that quantum mechanics, we just get infinity because it has a continuous spectrum. And it doesn't look anything like the black hole entropy that you might have expected. Sounds weird, right? What would it look like to compute the thermal entropy? So the Hilbert space is not like that. What would the thermal entropy look like? Well, if we computed the thermal entropy, we could do a Euclidean computation where we take our spatial slice, which ends on 2 of the ADS2 boundaries, and then we'll take the propagator and glue it all around like that, and we'll make a configuration that's called the double trumpet. But it will be the double trumpet with a labeled geodesic, because we started with the thing in this gauge-fixed form at t equals 0. We evolved by e to the minus beta h, and then we glue together and sum over the states. Okay, so it will be the double trumpet with a labeled geodesic. From the point of view of this thing as Euclidean manifold, well, because I'm computing, if I compute in that alluvial quantum mechanics, the trace e to the minus beta h, it means that I compute the propagator of the alluvial quantum mechanics, which is this object, right? This is the geodesic of length L and length L prime, and then I glue L to L prime with delta function and integrate over L. This is the marked geodesic. I do, but I do integrate over it, but that doesn't mean that I don't mark it. I integrate over L, but it's still marked, okay? No. I mean, I'm not gauging. I mean, I'm not sure if I understand, but I don't gauge translations in time, right? I do not. No, but the point about the marked geodesic is the following. If I look at this double trumpet as the Euclidean manifold, I can find another geodesic that connects the same 2 boundary points, okay? And so it looks like, from the point of view of counting the sum over Euclidean manifolds up to Euclidean diffeomorphism, that I've multi-counted the same double trumpet manifold an infinite number of times, labeled by how many times this can wind. Of course, each of them appears in this sum. So when I do this trace, I'm supposed to count this manifold with the white line, and with the green one, and with the one that runs twice, and so on. And indeed, the answer is infinity, and it better because the spectrum is continuous. But if I actually computed the JT partition function, Euclidean partition function with the manifold, it's finite. Okay, so that discrepancy is exactly because in this trace, you kind of count these geodesics. So you already see here a hint of something funny. It seems like although we fix the gauge in a perfectly good way from the Lorentzian point of view, right, requiring the spatial slice to be a geodesic seems to leave no gauge choice. It fixed the Hamiltonian constraint. Somehow, even when we compute the thermal partition function, and we think about it from the Euclidean point of view, it seems like we didn't correctly fix the gauge. Because in this Euclidean manifold, there's some discrete ambiguity. So locally fix the slice, but it has this discrete ambiguity, and that is, makes the answer infinite versus finite. So it has some big effect. Yeah, this is like a den twist. Yeah. So this is a little bit puzzling, perhaps. Okay, it's a sort of a hint of something funny, and we'll see much more kind of sharp versions of this in not too long. Yeah.
Sometimes, like when you can you still have some individual freedom? Like there is nothing like this.
Well, it depends on whether you look at this Euclidean manifold or in the Lorentzian manifold. So in that space-time, in the Lorentzian 1+1 dimensions, at least on shell, it seems that the gauge is unique, because if I pick 2 points here, here, and here, there is a unique geodesic which connects them. There's no discrete ambiguity, at least for the on-shell solutions. But when I put it together to compute the thermal trace, it looks like there was an ambiguity. Okay? Yeah. In infinite L, well, you can see that here because as it winds around and around, the length gets bigger and bigger. Well, it's related to the fact that the potential is not a bound potential, right? So the Liouville potential, right, looks like this, of course, and it's because it goes, it has this continuous spectrum at very large L. Yeah. Small energy. Yeah, small energy. Yeah. On the other hand, from the bulk point of view, there's something UV-like about this divergence, or at least some related divergences. Maybe I'll discuss it later, but if you do this computation, you can also measure this size, like the size of this geodesic, and the divergence is in a way related to when this geodesic is small. Although it's not quite precise, because here it's about this overcounting problem, so it's slightly different. But sometimes UV and IR get mixed up in interesting ways. So what I really mean is the following. If we go back to the space-time picture here, but sometimes UV and IR get mixed up in interesting ways. So what I really mean is the following. If we go back to the space-time picture here, when L is extremely large, then if I had some bulk heavy objects, some bulk UV stuff that I didn't incorporate correctly, it will be able to contribute to the answer because I can put it here in the middle, and when L is very large, it will be enormously redshifted as measured from this boundary. And so when these configurations with huge L are in some sense sensitive to the bulk UV. So there's a little bit of UV-IR correspondence or something. So it makes that discussion a little more subtle. Okay, so let me come back to this factorization issue for a moment, and then we'll move on. But anyway, so this sort of suggests that we didn't really fix the gauge correctly non-perturbatively, and I'm going to come back to that issue in a little bit. Yeah. Sure. Okay. I guess. The den twist doesn't change the manifold, right? This isn't a den twist that changes the manifold. It's just changes which slice. It's just that if I were studying this Euclidean problem, it would have been an invalid gauge to say that I picked the slice to be a geodesic. That's not a good gauge because there are many geodesics.
It sounds like you have complex saddles. Action cycle and the
it could be, yeah. I mean this. Well, these are actually it's slightly more subtle. So first of all, this thing isn't a saddle; it's an off-shell configuration. It turns out there are no saddles with these boundary conditions of this type, but because the theory is so simple, people could do this path interval exactly like exactly, but it's not actually a saddle. So, okay. Also, this is a real manifold. When we compute the thermal thing with real beta, this is a real manifold. And it's on shell in the metrics. I mean, the metric has constant negative curvature, but the boundary doesn't obey the boundary equation, the classical boundary equation of motion, so it's not a saddle. But it's an off-shell configuration, but you can still do the computation. Maybe there's a sense in which the saddle is at B equals 0. In other words, this thing switched to 0 size. This looks singular. But you can do the... You don't need... Because the theory is so simple, you don't need to evaluate the path integral with saddles. You can just evaluate it. But I think this issue of saddles is interesting. Maybe I might come back to it on Thursday. But... okay, well, anyway, let me...
Is simple doesn't mean that you should
No, I think they evaluated the integral honestly, but it's not guaranteed that it will be evaluated. I mean, you know, so first of all, this computation. So, well, okay. If you take this trace, you can evaluate this trace in the quantum mechanics. The answer is infinity. Okay. That's the end of that story. Now, if you look at this Euclidean manifold and you said, oh, somehow we shouldn't have fixed the gauge in the way we did, and you should only count the trumpet once and not infinitely many times, you won't get infinity. And then you can do the integral over this boundary wiggles and the integral over this modulus of the trumpet. That was done by said Shanker Stanford. Yeah, I agree. I agree.
Trying to compute another integral which responds to a different number of integrals respond to different numbers.
Yeah, probably. Yeah, probably. Probably. Oh, okay. Probably. Okay, so this answer is kind of funny, but the Euclidean theory seems to give answers that we would like better from the point of view of ADS-CFT. So in particular, if we were to evaluate the thermal partition function using Euclidean methods, the way we usually evaluate the black hole entropy in gravity is we would have computed something with the disk topology. We wouldn't have done this strange computation. We would have done this computation. And that can be done exactly. It was done by Stanford and Witten. There's some localization that allows you to solve the theory exactly. It's related to the Schwartzian theory of the boundary object. And let me just quote the answer. I'll write the answer in a certain way that I think will be the most useful. I'll write it in terms of the Laplace transform of the spectral density. Okay. So that was the answer found by Stanford and Witten for this disk path integral. And that answer looks nothing like this infinity. It's just an unrelated computation. Okay. So something sounds sort of strange. Now, one might have wondered whether, although the Hilbert space didn't factorize, you could try to split it apart. So, as I said, the whole story reduced to the quantum mechanics of the positions of the boundaries, and there are two boundaries. So it's, yeah. That's true. I'm not sure what you mean by better in this case. I mean, this answer looks like the black hole, like the Bekenstein-Hawking answer. It's also finite, whereas the other answer is infinity, and it doesn't have the structure of the Bekenstein-Hawking answer. Well, I mean, from the point of view of the quantum mechanics you get from canonical quantization, this disk computation is not computing an entropy at all. It's just computing the norm half of this. So this is just a meaningless normalization of a particular scattering state of the quantum mechanics. So this doesn't seem to have any interpretation in that quantum mechanics. Okay, so I'm just trying to emphasize that thinking about this theory in canonical quantization and versus the way we usually do Euclidean computation seems very discrepant. Okay?
But you could try to interpret it as a thermal trace in quantum mechanics if you associate quantum mechanics with the property.
Right. So that's exactly what I'm going to say next. But it doesn't work. But it doesn't work in an interesting way. So let me try to make that a little more precise. So we said that all of the dynamics was about the location of the boundaries. So we should have been able to write this Hilbert space as a Hilbert space of a particle or a point in ADS2 times another point in ADS2. Those are the two boundary points. And then we'll have to quotient it by the SL2R global symmetry of ADS2, which acts together on both of the boundary points, but it doesn't have any intrinsic meaning in the geometric variables. Okay? So this isn't quite a tensor product, but it looks like a quotient of a tensor product. So you might have thought that if I eliminate this gauge constraint, then I will get something that looks factorized and things will work. Okay? So this often happens when computing entropies or entanglement entropies in gauge theories, not only in gravity. And a nice way to think about it is we might have the Hilbert space of the gauge theory in the full space, and we want to factorize that. And in order to do that, you have to have some splitting map that maps it into an actually factorized Hilbert space. One example might be where this obeys a gauge constraint, and it maps it into the charge 0 sector of this tensor product, where this might have a non-zero charge and this is allowed to have a non-zero charge. Okay? That's basically what this quotient would try to tell you. Now, there's one tiny thing that's wrong in this, which is if I just took 2 points in ADS2, there's nothing to guarantee that they're space-like related. So maybe it's a subspace of this or something, but you might have still hoped that there was a map of this type, and if you turn the crank, you will get all the answers you liked, and this would look like the path integral, the thermal partition function of some single point in ADS2 quantum mechanics, which is equivalent to the Schwartzian quantum mechanics. So that's what you might have thought. And you will want this map, of course, to be an isometry in the sense that if I apply it and then go back, I should get back to myself. Otherwise, of course, if I will I want it to send a normalized state to a normalized state. Otherwise, if I apply this map and compute some Rayleigh entropy or just multiply the answer by an arbitrary number, that's not meaningful. Right? That's true in general. That wouldn't be true in this example because there's nothing wrong with the quantum mechanics of a single particle in ADS2. Okay? So that could happen, but it doesn't have to happen. Maybe another way of saying it, if we go back to the gravity language, is, we had this space-time. We want to compute some sort of entropy of just 1/2 of it. So really, we should imagine putting some boundary conditions here that cut the space, and we should pick a physically sensible boundary condition. And then we discuss the correct gauge invariant states in this left half, which has this boundary. But there will be more states than the ones in the full space because I might have sort of the total charge here and not match the charge here. But it's still consistent if I put some consistent boundary condition here. So this boundary condition is not meant to really be very physical. It's just like trying to cut the space apart with a knife. Okay? Some external thing I did to define this map. That's, I think, how we should think about entanglement entropy in field theory. This is kind of from work I did with David Kaltschmeyer, by the way, some years back. It's just the adjoint of this map, right? Yeah. But what does it do?
Behind the I dagger I.
It's just that this map should be unitary on its image. way, not multiply some of the states by some random normalization, right? Otherwise, of course, when you compute the entropy here, it has no relation to what you mean. If I end up, if I am allowed to map the state by non-unitary transformation, and then I compute the entanglement, I can get any answer. I could just multiply the state by 75, right? Then I will change the entropy by log 75 if I just sort of blindly turn the crank, right?
And this is enough to any I that's unitary or
In general, that's a good question, but here it's clear because if we think about it in terms of this boundary condition, what is the Euclidean computation of the entropies? The Euclidean computation of the entropy, including that little cutting map, will be to compute this. So this is the external boundary with inverse temperature beta. This is this extra boundary condition added. And the condition that I dagger I is that this is I dagger I, right? The bottom half makes I, the top half is I dagger. And if that's 1, it means that this little circle does nothing, and I would get the disk. Okay? So I dagger I equals 1 is the condition that this goes away, and the disk is a unique answer. Okay, but it turns out it's just impossible. And it's impossible for some topological reason. There are a bunch of different ways I could phrase it. But let me try to say it in what I think is the simplest ways here. Yeah.
Go back a little bit. Just after all that discussion, can you just repeat the statement about the Lorentzian computation?
Well, I mean, this Lorentzian computation gives infinity. But somebody might have thought that maybe, I think there was somehow a hope that this infinity was like counting the gauge orbit, and if you deleted that, you will get the disk answer. Maybe somebody might have thought that. That's not correct. Yeah, maybe disk squared, but it's not disk or disk squared, so, okay. I mean, maybe the logic here, we should have taken it in the other direction. We like the answer of the disk because it looks like the black hole answer. What could that have come from in Lorentz signature? The suggestion was maybe it came by treating the two boundaries sort of as two separate quantum mechanics, which means we split the original Hilbert space like this and then computed an entropy, right? So the original Hilbert space didn't factorize, but we can split the state and then try to compute the entropy, but that doesn't work, okay? In other words, this disk answer is not the thermal partition function of a Schwarzian quantum mechanics. That's part of the answer, but the thing that's mismatched is very specific. Let me say what it is, and then I think it will be clear. Okay.
Volume of the classical statistical mechanics.
That's fine, but you might have thought that it was the trace over the Hilbert space you would have gotten by quantizing the Lorentzian version of the Schwarzian theory, which is the same as the quantum mechanics of the particle in ADS2. And that turns out to be wrong for a very particular reason that I would just, maybe I'll just say it and then it'll be clear. Okay, so what is the, first of all, from the, okay, well, I can say it from the Schwarzian point of view first, since we sort of already jumped to that. So we might have thought that we were talking about a Schwarzian quantum mechanics times the Schwarzian mechanics, quotiented by a combined global SL2R, right? That's what the Lorentzian problem looks like, right? Where this is sort of the Lorentzian Schwarzian theory, where L means Lorentzian, okay? That's what the Lorentzian problem was. But when people say they compute, in Stanford and Witten or whatever, or computed this Schwarzian path integral, they're not taking the trace of this Lorentzian Schwarzian theory. And the distinction is defined, the basic variable is a map from the the time is measured on the boundary to reparameterize time. And the range of this is minus infinity to infinity, and the range of this is also minus infinity to infinity, no constraint. Okay? That's what this Lorentzian theory means. But when you compute this disk answer from the Schwartzian, you demand that your Euclidean tau lives on a circle, and F is a one-to-one map. Okay? This condition that F is a one-to-one map is non-local in Euclidean time. There's no local condition you can impose on F which will demand that when you go around the thermal circle in tau, that F, the image, wraps the image circle exactly once. Okay? It just requires the boundary as a smooth curve. So, you could add some constraint, like maybe the derivative of F is positive. That will, allow some windings and not others, but you can not just pick out winding one. That's not possible, right? And in fact, if you just take this Schwartzian mechanics, or equivalently the thing you get from that splitting, or those all lead to the same answer, and if I just take the trace, I will obtain the thing where the winding of F is 0, right? Because in the Lorentzian theory, there is no periodicity in T. So if I compute the Lorentzian propagator, analytically continue and glue it together to compute the thermal partition function of the Lorentzian mechanics, it will tell me that F is a single valued map. This actually corresponds in the JT language to this little circle surrounding something with a conical angle. And in the gravity language, you can say the same thing. So if we cut out this little hole with this boundary, how do you impose the condition that you didn't cut out a cone angle? That's not really an easy condition to impose. You could demand that the extrinsic curvature is 0. That will tell you that the total angle around it is 0. That would be a local condition, but it's not what you want, right? You want the angle to be 2 pi and not 0. So the thing that you naturally get by taking the trace is like the guy with cone angle, with the cusp, right? So if I just take the trace in this quantum mechanics, it's like the cone angle here is 0, kind of cusp geometry that looks like this. But what you really wanted, the disk, in other words, corresponds to this angle equals to 2 pi, and there is no local condition you can write that will pick out 2 pi. So there's some topological obstruction, and the real relation is that this disk partition function, or the Schwartzian, the thing that people call the Schwartzian thermal partition function, I'm just going to mess this up. The thing that people call the Schwartzian partition function, Euclidean thing, which demands that the reparameterization is a globally one-to-one map, in terms of this quantum mechanics, is like a trace with the insertion of some extra operator, which we think of as some defect operator that converted the cusp computation to the disk, sort of the operator that turns this angle into the flat plane. And you can write this operator very simply in terms of the Schwartzian quantum mechanics, because it's just the thing that shifts F by 2 pi, right? In Liouville theory, but Liouville theory is, I have to unquotient. I get Liouville after having done the global SL2R quotient. So I have to unquotient by that, and then I could describe this operator. Excuse me? No, in other words, Liouville quantum mechanics is 2 copies of the Lorentzian Schwartzian quantum mechanics quotiented by the diagonal SL2R. Yeah. And this operator lives in the thing before I did the quotient. At least that's where it's easiest to phrase. Maybe I could phrase it, but I'm not exactly sure what's the formula. It probably descends to the quotient, because this operator commutes, I think, with SL2R, but I'm not sure what's the formula. A simple way to think about it in the language of the Schwartzian mechanics is that this thing is like e to the, where this momentum is the thing that shifts the variable f by, it's the momentum conjugate to the variable f. So this just says that I shift the thing by 2 pi when I go around. Maybe I put it 2. Okay, but one can work out the explicit matrix elements of this operator and so on. Of course, in the full theory, I think what we will imagine is that in like the full UV complete theory. Well, I mean, not to say that these theories are not UV finite. They are, but they look there's something different about them than the true gravity. We would think that in the UV complete theory, we would get this operator by taking some partial trace over UV modes, whatever they might be, of the Hilbert space. So you might have thought that, so in other words, here's a way to make this operator. Suppose when we took this cut, we put a crazy boundary condition here with many degrees of freedom, like the SYK model itself. Well, we know that the actual thermal partition function of SYK model looks like the thing, the Schwarzian guy with the winding condition. And so then we can use that to impose this winding condition. Maybe another way of saying it is if you have a system with many degrees of freedom, it can keep track of the time. And so then you can impose a condition like that as a local condition, at least approximately. So somehow this is how it should work in the good theory, but I don't actually know an example where it works like that. Could you say it again? Yeah, I mean, it has some interpretation in the Minkowski theory, sure. I mean, well, I mean, in the the theory where I cut the space in half is the Minkowskian theory, and that operator has the simple interpretation there. I mean, it's the same interpretation that I said. It's just the thing that evolves you in this time by a certain amount. Except that you go in Euclidean direction, which is good because it makes this operator Hermitian operator, and it better be Hermitian because you're putting in this trace and you want to get a real number. Yes, yeah. This Minkowski. Well, it depends on exactly which boundary condition you pick there. There's some freedom in that in the paper with David. The choice we gave a slightly bigger phase space, so which is I think exactly related to one copy of the Schwarzian, and it basically looks like a more like, well, I mean I can just write. So you see if I think of 2 points in ADS2, if I think of 1 point in ADS2, it looks like it has a 4-dimensional phase space. So I should have not only the variables like L and its momentum, but one other conjugate variable. And so I have a Hamiltonian that looks roughly like the thing that I was writing. And then there's another piece that looks like this. I'll call this pi. Oh, well, this, okay. Q. Q is a momentum, maybe. bad notation, but whatever. And then, again, I get the last thing. Maybe it's just like that, yeah. And then there's another variable that I didn't write. So this is, you should think of this as the conjugate momentum to some other variable phi that doesn't enter the Hamiltonian. Okay, so that's what the model looks. It's kind of like the Morse potential where this coefficient is dynamical. So I guess I hit the hour mark already, even though I didn't really get to the main thing I wanted to tell you. But should I keep going, or should I just do it tomorrow? What do you want me to do?
It's logical to keep going.
Well, okay. I mean, I wanted to tell you about this work where we tried to add end of the world brains. In a way, it's a separate topic. So maybe I should just. Right. Right. Well, you know, can I explain it? Well, I think this is what happens if you take a theory that's so basically. It's a very special property of a bulk theory with gravity and other degrees of freedom that the usual long-distance Euclidean analysis we do is compatible with the usual long-distance Lorentzian analysis that we do. And if we write an arbitrary theory, it doesn't work. Okay, so somehow the Euclidean analysis often looks more compatible with ADS-CFT. But in a good theory, then its Lorentzian analysis should also be compatible, right? So what we ultimately want is, what we really want is a theory where we do the correct Euclidean and Lorentzian analysis of the same theory. We don't do something incompatible when we discuss the theory in Euclidean and Lorentz signature, and we end up getting the same answers. I was going to, at the end today, give you an example of how that could work, but the actual formula I wrote was in a context where I had added some end-of-the-world brane. The reason for that is, in pure JT gravity, you can never discuss the single-sided configurations physically. That's why we had to discuss here putting in this kind of artificial cut to just chop it in half. Because in pure JT gravity, there's nothing for the space to end on. That looks like an obvious pathology, right? So to make the discussion a little clearer, I was going to introduce some dynamical end-of-the-world branes. Then we can discuss single-sided configurations. And in that context, I was going to explain how, in principle, the Euclidean and Lorentzian analysis could end up agreeing. But maybe, I'm not sure if I can explain it clearly. I could explain it in a picture, but not with a formula, until I describe to you how the end-of-the-world branes work, and then maybe that will take me another half an hour. So I'm not sure what's the best. Why do we postpone? Yeah, I think that's basically equivalent to the kind of, that's an example of the kind of end-of-the-world brane I'll discuss, because the reflection plane will be a geodesic, so it will be like the rest mass equals 0 version of this end-of-the-world brane. Yeah. But in general, you can also put you can also put a mass at the reflection plane. That's the end-of-the-world brane I'll talk about.
By the variable that you introduced there, when you wrote the syntactic for P is just the conjugate.
P is the conjugate momentum to L, written here.
It doesn't have a geometric meaning, you just compute it what P.
Oh, I don't know. Probably, of course, it has a geometric meaning. I'm not sure exactly whether it has a simple expression like related to L dot. Yeah, it's. I think, given that the Hamiltonian looks like this, it's equal to L dot. Okay. So. But yeah, I mean, you want a more some curvature, yeah. 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 I think it's no. L is a geodesic, but it's at the boundary part. So L doesn't have to intersect the ADS boundary transversally, and in fact, it does not. So it's related to the angle that L intersects the. But I don't remember the exact formula. I don't think it's directly related to having two boundaries. It's a more general, more interesting than that. And indeed, well, tomorrow, when I introduce some dynamical objects where space can end, then we should think of those as single boundary configurations. There's an ADS boundary, and then, okay, the space ends somewhere in the middle, but that's okay, right? You know, for example, if we took, ADS 5, and we suppressed this, everything but the radial coordinate and the time coordinate, then the global ADS 5 looks like the R direction ends in the interior at some boundary condition, which is just the origin of polar coordinates. So we want to introduce some objects that allow this 2D theory to be like that. But that will not fix the problems. And I'll sort of explain next time how if you introduce such objects, then the Euclidean analysis a la SSS still results in a matrix model. Basically, looks like a matrix model with fundamentals. You can integrate out the fundamentals and get a deformed potential. You still have a continuous spectrum. In the Lorentzian analysis, you'll get something like you'll get the Morse quantum mechanics instead of the Liouville quantum mechanics. So exactly this potential with this Q being related to the tension of this brane. And so everything is quite similar. And it also has a divergent partition function. And that divergence does some interesting things in its contribution to in the Euclidean theory, when you sum over all topologies, including adding the dynamical end of the world objects, that divergence is present and has to be regulated in a certain way that I'll describe. That theory can be, you can kind of, again, make sense of the Euclidean and the Lorentzian theories separately, but they seem to be discrepant. But I'll draw the picture of the thing that will relate them, and then we're going to understand what this picture does next time. One of the effects, so from the low energy gravity point of view, you should think of, so here's my space-time. When I have the end of the world brane, I should allow myself to include gravitational instantons where I add little trumpets like this. Okay? It makes sense. We always include such objects like this. We should think of this thing as some kind of particle. I mean, it's almost like a particle, which happens to, it's an orientifold plane. It's natural to include these instantons. And then they change the effective gravity theory. Okay? In particular, they change the inner product, the naive inner product of states, because if we, here's our ADS boundary, here's the end of the world brane that we'll introduce next time. We were supposed to fix the gauge by picking a slice, but once I have instantons like that, it no longer the gauge is no longer uniquely fixed by demanding that the slice is a geodesic, which is orthogonal to the end. So you can have here a length L and here a length L prime, which are different, and find a solution like this, as long as I add a little piece here with, say, the end of the world instanton. Okay? Once I include this diagram, I should better include everything else. So maybe I include handles, and maybe I include a bunch of them. So, I should add up everything I have. And maybe I have some other UV stuff which is more complicated, and I add everything together. So this maybe has length B, and this is going to be some x of B, which maybe I don't know. Of course, in any specific theory, I could compute this. And it turns out, on the other hand, if I were to compute the thermal partition function, the answer in a general theory of this type is the disk plus the trumpet glued into the sum of all of the junk. This and this junk are the same, of course, because that's kind of the class of theories we're considering, where the metric always has this constant negative curvature. So if I add some junk in here, it doesn't affect how this piece of the manifold glues onto that base. So how does it work? Depends on what is this x of B. Suppose we have a magic x of B where this equals a sum over a discrete set e to the minus beta ei. I don't know I don't know a 2D theory with some brains which gives me such an x of b. Of course, we can find such functions, but I don't know how to get them from some sum over topologies. But if we had a magical theory which was like that and gave a discrete spectrum for the thermal partition function, if you plugged it in here, you will find that the matrix of inner products looks like the sum over energies of the energy eigenstates. Well, I'll write it like this. Okay? So if this is the answer here, then this will be the answer here. What does this mean? Well, this will mean that there are an enormous number of null states because the inner product is a projector onto the energy eigenstates of this discrete list. The vast majority of states are null, and particularly the orthogonal energy eigenstates that aren't in this list have zero norm. And so I didn't really fix the diffeomorphism constraint non-perturbatively in a theory like this through this choice of gauge. Well, you already see I did something that didn't really fix the gauge because there's an ambiguity in where I put this. Once I think about these instantons, I have to fix the inner product. And when I fix it, I find that I get the same discrete spectrum as I got from the Euclidean computation. So if I had a magical theory where this x of b gave a discrete set here, then the Lorentzian analysis will agree. Okay, so I think that's the reason why we, why things normally work, right? Why when we do the Euclidean analysis, in ADS5 times S5, we get the right answer, and it would in principle agree with quantizing the Lorentzian Hilbert space, but it's just hard to see because if you, naively UV completed your theory of supergravity in ADS5 times S5, like with some cutoff or something like that, which would give a finite answer, then I will be in a situation where this x of b doesn't lead to this exact horrible infinitely too many states. Okay, but I want to discuss it in more detail next time. I want to write for you what this wave function is, and then a little bit show you how it works. Okay.